So good afternoon. So we start now the last class of the day, and I'd like to introduce you to Dr. Noemi Pinilla-Alonso. She's Spanish. She got her formation on the University of La Laguna. No? She got her bachelor in physical science in 1997, and 2003 the master in physics of the cosmos. And finally in 2009 her PhD in physical science, summa cum laude, and also University of La Laguna. She has had, during the formation years, she had extensive observational experience using telescopes of observatorio del Muchachos. She got several postdoc positions after the PhD. From 2009 to 2011, she got NASA postdoctoral fellowship at NASA Ames Research Center. And 2011 to 2012, postdoctoral researcher at Instituto de Astrofísica de Andalucía, Spain. 2012-2015, postdoctoral research associated with Tennessee, Knoxville, USA. From 2015 to 2016, she got a position as a visiting researcher at Florida Space Institute in Florida. From 2016 to today, she is associate in planetary science at the Florida Space Institute. From 2018 to 2021, she acted as Arecibo Observatory Science Manager in Puerto Rico. From 2018 to 2023, when the observatory was closed, she was also the Arecibo Observatory Deputy Principal Scientist. And from 2019 to the present, she joined appointment as Associate in Planetary Science at the Physical Department at the University of Central Florida, USA. So several awards during their career. 2016, Severo Cho Excellence Visiting Professor at the Instituto de Astrofísica de La Laguna. 2017, she got asteroid named after her. The asteroid 10,689 Pinilla-Alonso, named by IAU. 2018, she got University of Central Florida Luminary Award for being instrumental in creating collaborations that have elevated the work done at the OFC Florida Space Institute, the Center of Lunar Asteroid Surface Studies with the College of Sciences, and at the Arecibo Observatory, Puerto Rico. 2021, Women in Story, both honorary, an award for women in recognition to their impact on students of the UCF's campus community. And finally, in 2022, our County Distinguished Resident by Mayor Jerry Dennings. During her career, she was very active, mentoring and supervising of students and young researchers, as well as extensive in public outreach activities and projects. Her interest in sciences lie in the discovery how our solar system formed and evolved to its present state. In particular, determining surface compositions of minor bodies, interpreting them in terms of surface alteration mechanisms, and ultimately formation conditions with special attention to the ice-rich solar system bodies. One of her most recent projects involves the use of James Webb Space Telescope to study solar system objects. She is the principal investigator of a large observational program that was approved on the first observational cycle of JWST, entitled Discovering the Decompositions of the Trans-Neptunian Objects, Ice Embryos for Planet Formation, DISCO-TNOS, with around 100 observational hours awarded. This project has been producing really incredible data that will have a huge impact on our understanding of solar system formation. So it's a great honor to have you here, Noemi. So please have the floor.
Obrigada. Eu não vou falar português porque almost the only thing that I can say is a borboleta é ótima. Eu vejo uma borboleta. And I don't think that it's going to apply to what we are going to do today, so I'm going to switch to English, but I'm trying to practice. And I think this is going to be, I'm telling you in advance, the worst class that I'm going to give, because I'm not planning to talk about what I know and what is my specialty. That is, as Georgie said, ice in small bodies. I'm going to talk about things that I don't know and I've been learning recently, because I think they are really important now. I mean, it's something that I knew before, but now is when I really realize how important they are for what I specifically do and how interesting they are. And I think we are at a moment where we are going to build those bridges stronger than ever. And that is what I want to deliver in my first presentation, and you will understand later on what I'm talking about. So this would be typically, okay, no, this maybe. Okay, why is not working? Let's start again. Escape. Now you cannot see it. I have to go to Zoom again. Share screen. Presentation. Okay. Here. Yeah. This would be when I talk about me, myself, and I'm not going to sing, and Giorgio already introduced me, so I'm going to go through that. But this is basically what he has been telling. I've been scattered around this world a little bit, and that has happened. I lived 3 months here in Rio de Janeiro in 2011 after my first postdoc that I loved. Not my first postdoc, Rio de Janeiro. And the only reason why I've been going around the world is because I've been chasing ISIS. That's what my PhD was about, and I started to love it at the moment, and I still love it. So it's kind of what takes me from one place to the other. And why small bodies? This is something that I've been including in my presentations for a long time. And it's one of these slides that made me realize now some things, you know. Everyone here, I don't know, how many of you are interested in planetary science? Okay, there's a bunch of you. How many are, for example, interstellar medium, molecular clouds? Nobody? Ah, I'm lucky. And so, disks, debris disks, anyone? No? Okay, one. Okay, good. So every time that we talk about the small bodies, it's like, okay, there are so many things in the solar system, Jupiter, Saturn, the moon, we can go there, Mars, there is water, there is no water, everything. Why small bodies? Where even if they are the icy ones, there is not so many things that you can observe. So I always had this prepared there to explain why are we so interested in small things, the small bodies. And none of them are true. The small bodies contain material that is mainly unaltered from the origin of the solar system. We always say that, and it's true. So it can reveal, if we really understand what it is made of, we can know which were the conditions in the nebula where the solar system formed and the materials that were dragged from there. It also helps us to understand these first steps in the formation of the solar system. And I mean, even if the materials are a little bit altered now, we can know more about where the objects formed in the solar system and which materials were at each different distance, and all of this fuss around of bodies being scattered and the late heavy bombardment that is more related to dynamical studies. So our results, when we observe small bodies, can provide constraints and initial conditions for those models. So all of that, you even say, and this is really very good when you want to put together the broad impact of a proposal. Addressing the presence of water and organic compounds is of crucial importance to understand the origin of water and life on Earth. It's true, there are many things that we still don't understand on how we pass from the CHON molecules in asteroids or meteorites to the ones that would give the origin of life and everything. So there are things that we don't understand. But it's true that the materials, the objects that I'm studying are the ones that are rich in water and are rich in complex organics. So if there is life origins on any object in the solar system, would be probably in those that contain these materials. And another big scope thing, if we understand our solar system, then we will understand better exoplanets and other solar systems. So all of the reasons that I have always had them in the back of my head, like this is important for all of this, are things those things that I'm realizing now, that they are about to happen. These connections that were very broad are going to be narrowed in the next decade, and I'm pretty sure of that. So that's why I was asking how many of you know about molecular clouds and interstellar medium, because it's that thing that I don't know I am learning that I'm going to be talking. So now that I know you are not experts, you cannot correct me. You have to believe me. This is a little outline of the first part of this class. Basically, I'm going to talk about the origins of ice in space that are in the interstellar medium and in these molecular clouds, and how that ice is formed. Because I study the ice when it is already on the surface of bodies, and we will say, oh, it comes from the interstellar medium or from the cloud. How does it form really there, so that it ends up being a crucial component of small icy bodies? And I'm going to present results from one group that published early this year, an amazing paper that studies the molecular clouds, dense molecular clouds, using the JWST. Good, so, again, this is another amazing result of James Webb. This is an observation of one house using the coronagraphic mode, so that you fade up the star to see all that is around. And it was already known that Fomalhaut had a ring around, a disk, but the resolution, the image resolution of Webb, and the fact that it's observing in the infrared, gave this incredible result. So what you have here really is 3 rings, 1, 2, and 3 here. You even have concentration here of material that is probably a planet that is forming. So this is like a really Polaroid and a snapshot of what could have been our solar system when it formed. Well, it was only 2 rings, not 3, but it's very close. And also because we know from how we know that at this distance, this is not an asteroid belt. This is an icy objects belt. So it's similar to our Kuiper belt. You know, so we always think on asteroids are the things that we know better, but are there? It's only 30 years that we observed the first TNO that is not Pluto. But we know now that around the exoplanets there are also Kuiper belts. And the distributions of rocks and ices through our solar system is hypothesized to depend on how and where they originally form from the solar nebula. That is the same that is happening there, depending where these objects are orbiting now. When they are forming, it will determine their composition when the process of formation ends. So, where do the ices form? They form in molecular clouds. More dense molecular clouds or protostellar clouds, they have different density of hydrogen, that is the vital element. They have different temperatures, and there are inhomogeneities. That is how we know that our solar system started forming, about some kind of inhomogeneity that causes material to start concentrating and aggregating and everything. And in these clouds, there are formations that are dark clouds, that are denser, and is where more material is aggregating. And this has been observed. As you can see down there, this is an Alves et al. Result in 2001, and this is Barnard something. I can't see my comments, so I don't know the specific name. But is there, in that dark region, is where more formation of aggregation of elements to form molecules is happening. And the cooler it is, the more ice is able to stick to the different grains of dust that are around, and the bigger the molecules will form, that will end up being the pebbles and the ingredients of the different planets when the star forms there and we have the disk, that is the next stage. And this is kind of a representation, okay. So you know that the most abundant material in the medium are not ices, are the silicates. And these small particles of silicates, microns of them, they are moving around in these in these clouds, and the ice is when the temperature and the density is the appropriate for each of the ices, depending on their sublimation and condensation temperature, they will stick to the material and they will start forming. We will see how. So this, what I'm going to describe here, is how the models for the formation of ices explain that this process happens, and it's something that it has been from very long time supported by observations. This is not nothing new. There are a lot of things. I'm sure there are a lot of open questions still in this field, and then there will be more when we start analyzing the results in the infrared. But at least there are many important things there that have already been observed. So the different stages that I'm going to show have a difference in temperature and a difference in density as the materials and the elements are being dragged from the cloud. So the first phase is typical, is called the polar phase because it's when most of the H2O is formed and the NH4 plus maybe the NH3. These molecules are polar and they are formed by the simple elements aggregating and forming simple molecules. These are the lightest ones that you can have at the very first stages of formation of the ices. And typically they characterize the different epochs and the different phases with the temperature of the cloud, the density, and the extinction coefficient. The more dense, the more materials you have, the more extinction there is on the sideline. Then it's also the H to H2 ratio is important, and then the ratio between H to other elements like oxygen or carbon. And you will see that. In a second phase, I mean, here I said the most abundant molecule from here is the H2O, and these others that are formed are intimately mixed with the H2O. Then here we have the grain, we have this layer that we had before, but also there is more formation of CO2 and CO now. Okay, this formed there, and so the relative ratio of H to H2 and H to CO starts changing and moving around depending what is available in the cloud. Next one here, this is an important phase. CH3OH is kind of is very popular in the TNO's area of research, and it's very popular also for people working in interstellar medium. And it is because it's the first CHO molecule, the simplest that can form, that will later on evolve on more complex molecules. Okay? So at this stage, the CO gets frozen. We can find the pure CO2 also, and then there is some formation of CH3OH. And one important thing here is that these two epochs, they happen kind of fast, so that any influence from the cosmic rays or the ultraviolet are not so important, because the process of formation is faster than the time needed to cause an effect by irradiation. So now we have already we have passed through the most simplest epoch, then the CO2 and the CO, and then the most complex molecules that give as a result also not only methanol but H2CO, HNCO, OCN minus, and later on the complex organic molecules that are also very popular in all of this field. What is happening in this epoch? The temperature inside the cloud decreases, and the density of molecular hydrogen increases from one phase to the other. This is the grain surface chemistry phase, and the next one phase is the thermal processing phase. This is very important also because it's when the heat is going to start affecting the elements, and that is something that is very interesting when we are going to see results from web, for example. Is not the only important thing is not the new detectors. The new detectors make the headlines. They are very good, like like water is detected for the first time on the surface of Mars, for example. First time, very popular. But if you can investigate which is the state of that water, if it is crystalline or amorphous, if it is mixed with other materials, if it is in very small particles or if it is in large slabs, all of that chemistry and physics is associated with different processes and different conditions, and it's going to tell you even more than just a first time detection. And this is something that is important in this phase. We already had CO2, we had methanol, but what is happening here, that now the temperature and the irradiation is going to start affecting these ices, and they are going to sublimate, for example, the simplest, the ones with the lowest sublimation temperature will sublimate earlier, and then they will trigger formation of other enrichment on the other molecules that are around. Like in this case, the most volatile would be the CO. Then also, if we keep warming up, remember that I told that in this layer, these ices are intermixed with the water. But at a certain point, if you keep raising the temperature, the materials will segregate, and they will no longer be intimately mixed. And this is important because if you have CO2, it will sublimate when the temperature is appropriate for the CO2. But if it is mixed with water, it's kind of protected, and it can survive temperatures higher than its sublimation temperature because it's intermixed with the water. So the state, again, will tell you things about temperature and everything. And remember that these are models, okay? Sublimation and segregation. And then finally, if we keep irradiating things, and as the temperature of the star the star has forming and keeps increasing and keeps blowing things out, then we have really processed complex organics that are these CHON molecules. They are very complicated chains or rings where we have a lot of carbon and the hydrogen that is free around or not, or by radiation recombinates, and they form very complicated materials that are less active. It's more difficult for them to get engaged in the chemistry and in forming other materials. Okay, so these are the models, and you can tell me the time whenever you want, okay? Not every minute. So this is the temperature increase phase as the onset of the star is affecting everything around. So, I already mentioned that there have been a lot of observations in the previous decades that have confirmed several points of these models. How do we know? How do we detect these ices? So typically to observe the clouds, people observe stars in the background when the light crosses that cloud. So you can see the effect on the spectrum of the star of the materials that are in the middle. That means that the light is attenuated, and that you need bright stars in the back so that you can get still some light on this hand when you observe from the ground-based telescopes. This here, for example, is a massive young stellar object. This is the spectrum, and all the spectra have a kind of a continuum. This typically tells you the color. The flux of the sun. No, this is not a solar system. Sorry, this is a star. So there is a continuum that is telling you the temperature of the star and all the standard things. But then we have absorptions here that reflect what is on the cloud. So this here is a pure model for water ice, so that you can see how many bands water ice has in this wavelength range. So we are here going from 2 to 5. 5.2 is more or less where NIRSPEC at JWST observes, and then up to 28 is where MIRI, this is 30, so around here is where MIRI goes in the mid-infrared, and this part we don't observe it with the web. But still you have, water ice has a lot of different combinations and overtone modes. Then the combinations and overtones are mostly at the shortest part of the spectrum. In the intermediate, we have the stretching vibrations, and from 6 to 30, that is more or less MIRI, we have bending modes and liberation vibrations. All of this jargon means that there are, depending if the you have the different atoms and they are linked one to the other, and these are like arms, let's say, depending if you are being pulled or you are being bouncing or you are being circling around, whatever molecular spectroscopy tells you, is one of these different modes that you can observe at different wavelength ranges. So as it's saying here, especially JWST is very powerful for this weather region to penetrate the dust on the cloud and to give high quality observations. These are not done with web. These were 1998. Let's start going through some specific molecules that we have talked before. This is, for example, water ice. This has a fundamental absorption here at 3 microns that is really powerful, really broad, kind of very easy to detect, even if there is a small amount of water ice, but it also has different properties depending what is around. So the band that would be, if it was pure amorphous water ice, for example, would be the green contribution here. You see how in this spectrum has an excess here or an absorption here that you have to try to fit with models or compare with reflectances to know where it comes from. In this case, it is explained with H2O intermixed with NH3. That is another of the light molecules that we said were formed in the preliminary stages. Then also this shape is typical when you have large grains of water ice. So here you have like different spectra, and you can see the variability when compared with this same model, the variability of the shapes. All of that is going to give you different information. Yeah, I went through all of this. This is another material that is very typical, that is the CO. We talked about that, how it is, when it appears is important, but also when it starts freezing out, and first when it triggers an enhancement of CO2 and then it freezes out and it doesn't evolve anymore. The band of CO2 is at this wavelength, typical of near spec, in JWST. And I will explain in the talk tomorrow a little bit more of the instruments and everything on the web. The yellow symmetrical absorption here is the typical fundamental of CO. But as you can see in this spectrum, it's not the shape of the spectrum. We have different contributions again as before. In this case, we have here a small contribution that is attributed to CO mixed with apolarized, like CO2, for example. It's probably CO2. And then, no, the CO2 is apolar. And then a mixture with a polar ice, probably CH3OH, that would cause this deviation here from the symmetry of the yellow band. So again, studying this band, you can start to see if, okay, there were phases that were poor on CH3OH. If we have this, there is CH3OH, and we can confirm some things. And again, here you have different spectra, and you can see the different importance of the two contributions that we have mentioned before to this green symmetrical CO band. Depends also on temperature, so it's also going to tell you the temperature of the cloud. Another interesting absorption, methanol, I told you, is one of the cool guys in the patio, and is the earliest signature of complex organic molecules. That's why it's so interesting. The fundamental absorption that we typically look for is at 353. This is small here, but it's the deepest one. We even have detected, we think we have detected on TNOs methanol at shortest wavelengths with the overtones, so where this band would be way deeper than it is on the overtones. But as you can see here, this is the 353, and is present in all of these objects, but there are other contributions here that are also interesting to study, and in this case are attributed to this band is due to a CH stretching. This is reflecting different CH stretching in very complex molecules of organic material. So these is the region of the aliphatic and aromatic bands. And there are many others that we mentioned that are forming the later stages and are important. So an OCN minus at 462, OCS, the sulfur species are kind of wanted in the solar system. We look for them in TNOs, in Trojans, in Neptune Trojans, thinking that there are hypotheses that say that it's a very efficient reddening agent on the surface. Then CO1, CO2 that we have mentioned, but also the isotopologues, the ones that are formed with a certain carbon, not with the other. And the ratio between these is important because this sublimates faster than this, and also not only that, this is heavier because it has one more carbon, so it's going to be retained easily on the surface of the bodies. And when we talk about small bodies that don't have very big gravitational forces, it's important to know if the objects will be lost or will be retained. And then the carbonaceous, aliphatic and aromatic carbonaceous molecules. So I'm going to talk, this is not my result at all, but this is what was published in January, and it's a really cool result, and this triggered my interest in getting to know a little bit more about the process of formation of the ices, not of the formation of the TNOs. Belongs to what was called the Early Release Science Program of the JWST. This call was in 2016, I think, and it was meant to be the first programs executed at the JWST, like to commission a telescope, or during commissioning. And they wanted to approve 3 or 4, I think it was 4 different projects that would kind of prove all the observation modes, so that the community could learn from them and put better proposals for cycle 1, 2, everything. Then everything was delayed, and it was convoluted, and we had to submit the proposals even before this was observed. But anyway, the fact that they were observed in the first 6 months means that they have been the first publishing also. So what did Melissa McClure propose to do? So, I mean, it was executed in the first 5 programs, it was selected, I already mentioned this, and it was a proposal for only 1 star, okay? And it's a very big program with 80 plus collaborators distributed all around the world, because when you want to do large things, you probably need large teams with a lot of expertise, most of the times, at least in the current size. So some results. What did they do that they couldn't do without Webb? So they are Webb observes in the infrared and observes from the space. So it can penetrate the dust way better than when you're observing the visible, like Hubble was observing, and because it's not ground-based, the atmosphere is not a problem. So you can really cover all the wavelength range that each instrument covers. So what did they say? Instead of studying, this measures the extinction coefficient, so they observed 2 background stars in the background of the cloud that were at high extinction. Before that, from ground base, you could only observe the ones that were in the regions where there was not so much dust, because if not, you wouldn't see those stars. They were invisible from ground base. So if they were before at AV9 or AV10, now they were going to 60 and 95, what means that you're going to find way more materials in the spectrum. And they observed with near spec 2.7 to 5.3, and with MIRI 5 to 14. Only this mode, the low resolution. This is the low resolution mode. The high resolution mode is the one that goes to 28. And this is a very schematic shape of what they found that we are going in detail now. So yeah, they did high signal to noise, measured at 4 microns. That is were probably a worst case scenario for them, and higher at 7.5. Yeah, because the low resolution mode has the lowest sensitivity at the shortest wavelengths, then it increments. And the questions were, which new ices we can detect, and what I was mentioning before, how are these ices mixed? What these ices are going to tell us about all the process and all the models that we mentioned before. So, again, this is very good. This is if you want to go to where you have to tell them you want to use their excellent toy, unique in the world, to do things that could not be imagined before, that cannot be achieved with any other tool. So this was the deepest ever background star observation. So another question that they're going to do is how does ice chemistry change with extinction? Because as I mentioned before, they were only achieving observations with very low extinction. So this was the publication that came out in January, and it was very cool because I had organized a nice seminar, a class this semester on ISIS at UCF, and just the day after they published this, we had the seminar by one of the co-authors of this paper, so she could explain everything to us. And this is the nice graphic that web does, but you're going to see way better things now. Oh, sorry. How am I doing? 50? 15 minutes, okay. Okay, these are the spectra of these two stars in the background. They did two at the end, and it goes, as they mentioned, from 2.7, they are showing here, to 14. Good. So what are we seeing here? This is the very broad band at 3 microns that corresponds to the H2O stretching mode. The one that is, you get bored of that. Before, we couldn't observe there. After 1 year of seeing the TNO spectra, like, okay, what did I say? Let's go, next chapter. But also, they can see, for example, here, this is the fundamental band at 4.27 of CO2, and this little one here, I will mention that in the next slide, I guess, because it's not labeled here. They also see this asymmetry here, that they, this is the 3.35 region, so there could be some methanol there, but also probably some NH3 molecules. And remember that the methanol was very specific of one phase of the clouds. So if we have it here, it's telling us already in which phase this is, or at least in which it is not. Then more H2O, more NH4 with CH3OH, methane, here, this was a first time detection, and also here, NH3 here, more methanol, and the continuum, you get it with silicates, okay? So, this, let's go a little bit more in detail here. The CO2, this is the little bit that I was telling, this is the isotope log. 13 CO2 and a lot of CO2, as much CO2 as you can see it even for the overtone. The overtones are way fainter, they absorb way less than the fundamental. So if you see it here, it's because there is a lot of CO2 here that is out of it now. But also, you see this? We can see this formation here on the left of the CO band, and this is not. Remember that before for the CO we used a blue component that was a little bit of CO2 and a red component that was methanol, but this is out of the limit where this CO2CO was. There is another material that absorbs at 4.6, that is the OCN-, another one that was mentioned in the potential materials to be found there. Then a little bit of a hint of a band here is more clearly seen here, and this is where the sulfur species with the oxygen and the carbon happen. So all of these that are marked here are first type detections, and I'm not going through this because this is some kind of weird linkage of the atoms in H2O that I don't know how to explain. I didn't study so much. It's called dangling H2O or something like that. So I think all of this detail is listed here. Yeah. Okay. And this is, well, first, you can see that this is irregular here, so it may have some contribution of CH3OH there or any polar molecule. But this shape here, this little peak, that's what when you observe with a telescope in the space that is so powerful and you have a signal to noise of 200, every peak can be abandoned. You just need to have a good justification for that. It needs to make sense. And this little peak, they have studied it in different spectra, and they are going to explain it in the next slide here. So this was a work from laboratory. We learned a lot of our observations. We can interpret them thanks to laboratory studies. They are really important. If there is any chemist here, you know you are wanted and we love you. Because if without that, there are many things that we cannot explain. In this case, for example, this is the fundamental of CO2, and you see how these different lines that are associated with different extinction coefficients, you can see this formation here on the left. And you can see also how the more we get this peak here, the broader this part here is. These are indications of different scattering and absorption properties that are related to the size of the particles or the optics, what happens on these materials on the surface. And this one here is this little peak here. So for the first time, this that was hypothesized in 2022, it was detected in 2023. And this is what this amazing result got. And I think it's a very nice Nature paper, so it's very good to read it. By the way, I was telling you this tells you the size of the particles, and the conclusion in this way, in this observation, is that remember that these are size of particles in the cloud, and they are already 1 to 3 micrometers. These molecules. And this is really what dragged me to this paper. This is what the title is the ice inventory or in molecular clouds. And this is really important because this is going to tell me that the study objects that have formed in that cloud, if I detect something, would this be expected? Does this exist in molecular clouds? Because if I detect something that has never been detected in a molecular cloud, then maybe it's another thing. And this is what I have been using these months to interpret my spectra. So here you have absolute density, column density of H2O in the two objects observed in this project, and here is the measure that they had before in low, less dense molecular clouds. You know, these are the high density, opacity, 95 and 60 magnitudes, and this is what they could achieve from ground base, that is 19. So, in particular, for all of these materials that we have seen in the spectra, and they can measure the abundance, they are more abundant in a high opacity molecular cloud, in a cold molecular cloud, for most of the materials, except for this one that is the OCN minus. So they are probably already trying to write the history of the OCN in these molecular clouds in a different way, because they were expecting, based on other observations, to have a higher abundance, and the abundance is lower than that. So why this is happening is something that they will have to explain now. And here is the ratio of each of these materials compared with the H2O. How the H2O is the most abundant, that forms at the beginning, so the ratio of the other respect to that is going to tell you how much of that water has been destroyed or is kept, and how much of the other chemistry is happening. And this is the picture that comes from there, the inventory. This is very useful to explain the ices in disks and in solar system objects and even comets, for the people that study comets. So, just because I've talked so much about this, I want to close with the last sentence of this paper, that is a reminder of why should I care about all of this if I am a planetary scientist. So these new capabilities, the JWST new capabilities, open the door to understanding the formation and inheritance of these key CHONs species through the star and planet formation process, and ultimately address what role they will play in shaping the chemistry of emerging planets. So this is the link, this is the bridge, and this is what brought me to talk today about something that I don't know, but I'm learning. So, and I hope to learn more in the next years based on all of these results. I had a little bit more to go back to solar system, but it can be in any other day. So, yeah, we can leave it like this now. And if I've talked about something that I know, you have to make questions about that. You don't have to be shy. So now it's your turn.
So, thank you. So, thank you, Noemi. So, questions?
Noemi, you showed a picture, a figure of two models with different parameters, with different ASTs. What's the difference between these two figures with these two groups of models? The reddening is the same, the reddening variation is the same in the two figures.
Maybe the size of the particles?
Ah.
Depending on the size of the particles, you have the effect or you have. I'm sure of the detail, but I would say it's probably that because what they are trying to show.
Okay.
Noemi, what is the difference between the gray spectrum and the color spectrum?
Two different sources. They also have two different objects at different extinction coefficients. One is 60 something, the other is 90. So actually the one that they study more is this, that is probably the one at 65, that is 20.
More questions? No? So, one question. You showed the initial formation of the ices. And then the initial formations, can you put in the slide, please?
The phases or?
The first phase of the, yeah, way before. So yeah, so this lesson phase, the temperature is over 20 K, but then the temperature is lower the other phases.
Yeah, it gets cooler.
Yeah, it gets cooler.
Decreases.
Wow, interesting.
And the density cuts up and the opacity is large.
So this is on molecular clause, no?
Yeah.
And then you have the collapse to form something like a solar system.
Yeah, that is when the protostar appears.
Right.
Then the temperature starts rising.
Yeah, and the opacity gets lower.
If the temperature didn't decrease, then you will have more ices.
Right.
Because the CO is more volatile than the H2.
So the organic formation happens on the stellar, the molecular clause or after on the collapse? The organics. The formation of organics starts on the molecular clause.
Some of them may form here, like for example, you have HNCO, but again, the other phase is temperature decreases. But here, the temperature increases.
Mm-hmm.
This is when the radiation, the thermal processing like the protostar starts to be important.
Right.
And then it's when you really have, is when the cosmic rays, the ultraviolet, all of that is important,
Mm-hmm.
and processing the surface.
Right. So that's fascinating.
I
Very interesting.
recommend this review paper is very, very good for
Mhm.
all of these cases. Because all that I observed.
All right. So any more questions? Don't be shy. No? So let's take Noemi again.